Hello Physics Nation, my name is Nate Larmond, and I'd like to do a torque problem provided by Openstax 9.3 9.4. It has to do with a car on a drawbridge. Here's the original text. We have a 900 kilogram car on the bridge, and the center of mass is halfway between the hinges and the cable attachments. The bridge is supported by the cables and the hinge. Find the force in the cable, and we're going to find the direction and magnitude of the force exerted by the hinge on the bridge. Sounds complicated until you look at the diagram. So here's our hinge. Here's the center of gravity of the drawbridge itself, and we're going to put a car right there. They said it was right in between the hinge and the cable. The entire span is 9 meters, 7.5 plus 1.5. So that means we're going to put the car 4.5 meters away from the hinge. This is my diagram to summarize what's going on. There's the weight of the car, there's the weight of the drawbridge, there's the tension applied by the cable, and there's the reaction force provided by the hinge joint. So I wrote a separate diagram just to sort out, if this is our pivot, how far from the pivot is this force? How far from the pivot is this force? How far from the pivot is this force? So the second diagram is just to identify all of the lever arms. And if there's no angular acceleration, that means the sum of the torques is 0. So here's the torque provided by the weight of the drawbridge. This force, this distance away from the pivot. And here's the torque provided by the car. This force multiplied by this lever arm. And here's the third torque provided by the tension. But the tension is not perfectly perpendicular to the lever arm. We only want a portion of the tension. We want the vertical portion in this diagram. That is the perpendicular portion, because we're doing the cross product. How do you get the perpendicular portion? Well, it's hypotenuse times sine of theta. At this point, the physics is done. We simply substitute in all the known information, grind out the algebra, solve for t, and it's hidden. Okay, 13,213 newtons. Part B is much more challenging. Part B asks for the reaction force from the pin joint. So now we're just going to go back to F equals ma. If there's no linear acceleration, that means the sum of the forces is 0. So we do the sum of the forces in the horizontal direction. That is the x component of the reaction force. That's this leg right here, the adjacent leg. Hypotenuse cosine of theta tells you the adjacent leg. And we just found the tension in the cable. There are only two horizontal forces. This is the hypotenuse. This is cosine of theta. 3/4 of the tension is pulling left. That has to be perfectly canceled by the horizontal portion of the force, except we don't know theta and we don't know the force, so we're stuck. That means you have to go to the y direction. So we play the same game. There's a y component to the force. This is the weight of the bridge. This is the weight of the car. And this is the y component of the tension in the cable. So you grind out the algebra, and we're sort of stuck again. We have the force provided by the joint multiplied by sine of theta equals this. Well, the trick is we have two equations and two unknowns. Here's the bottom line from the x direction. Here's the bottom line from the y direction. You solve for f and then set them equal to each other. So you end up with sine of theta divided by cosine of theta. That's tangent of theta equals this ratio. You undo tangent with inverse tangent. So I'm getting the direction of this reaction force to be about 68 degrees. And you plug that back in to the sum of the forces in the y direction and solve for the force. And so there you go. The pin joint exerts 26,814 newtons at 68 degrees above the horizontal. Thank you, and see you in the next video.